Hi everyone, and welcome to the Art of Dark Matter, where tonight we'll get to create some dark matter inspired art and hear from some experts in the world of both dark matter science and art. So I've been talking for a bit. I'm Mark Richardson, the Education and Outreach Officer for the Arthur B. McDonald Canadian Astroparticle Physics Research Institute. That's a collection of scientists, universities, and research labs across Canada trying to uncover some of the biggest mysteries in the universe while looking at some of its smallest things. And so I'm here in Kingston, Ontario today, and I'm an astronomer, and I study galaxies. This is actually a simulation I was involved in floating behind me. There is a video version of it, but I thought that'd be a bit too distracting. And so, galaxies are pretty cool. Dark matter seems to play a pretty important role maybe in holding them together. And we'll hear a little bit more about that and maybe pull it into your art. Science with everyone. And this is like the favorite part of my job here at the McDonald Institute. And I'm pretty excited about this event in particular because we get to bring art in as well, where artists also try to represent the universe around and in us. So I'm happy that even during these difficult times of COVID, we're able to have these events and people are joining in live or after the fact. So hello to everyone joining from home, whatever lands you call home. And again, for me, home is on the lands of the Cataraqui, the now Kingston area, the traditional land of the Anishinaabe and the Haudenosaunee peoples, and many Indigenous peoples before them. And I'm truly appreciative that we were able to learn tonight from our respective homes. Personally, I'm a settler from Halifax, Nova Scotia, the traditional land of the Skin Dressers District, the Mi'kmaq, and once the home of the racialized community of Africville. And so I reflect on that because my ancestors took advantage of these people in the removal of their access to those lands. And so, even today, some settler fishermen are preventing by force the Mi'kmaq from the rightful access to fish and lobster in those unceded waters. And the Canadian Supreme Court has upheld their right to hunt and fish, yet these rights are not being accommodated. So I think it's something to reflect on quite a bit. And then as an astronomer, someone who revels in the wonder of the land, the planet, the skies, and the universe, I recognize that this science in particular relies on facilities that use traditional and sacred lands of Hawaii and Chilean peoples. And these people must be included in this science and become the gatekeepers to those spaces. And I reflect on these histories as they are part of my identity, and part of the privileges that define me. So, although difficult via online streaming, I do look around often during these events to see who in our communities face barriers to participation, and I commit to helping to remove those barriers. And I recognize that from my place of privilege, I must listen and learn from those whose lived experiences include times of exclusion. Science is the pursuit of truths, and we're going to get to hear about some pretty cool science today. And obviously these endeavors cannot work if society is not treating everyone equitably. So to all of you at home, as you join in, I urge you to think of your connection you have with the land around you and the gift that we have to learn and create wherever we are. And so particularly tonight, when you're busy at home creating your art or wherever you are, reflect on your lands. I encourage you to reflect on your lands and the space around you, including the dark matter that is all around us. Okay, so the plan for tonight is to encourage us to take kind of a new opportunity to think about the world in different ways. Ultimately, I think it's important that art and science recognize their shared role in how we go about making meaning of our existence. So I wanted to highlight that this event is actually part of the broader Dark Matter Day international event that's taking place. And it's taking place, I know, in many countries around the globe. And so this is really an opportunity, I think, where people are really captured by the mysteries of dark matter. And so I recommend you check out the darkmatter.com website to see other events that you can tune into. Particularly like with COVID, there's no boundaries anymore. I know I tuned into a really cool talk coming out of the US earlier today. So I recommend you look there and see what events are on if this is the kind of event that you enjoy and you want to hear more. So Art of Dark Matter, tonight's event is also connected with a new exhibit coming to the Agnes in January. It's called Drift, Art and Dark Matter. Drift is an artist residency program that had 4 artists come to the McDonald Institute, the Agnes Etherington Art Center, and Snow Lab to have extended conversations about dark matter science, similar to what we're going to be able to do this evening, before then creating their own art. Drift will also be featured on the Agnes's website, so make sure to check it out if you haven't already been able. If you aren't going to be able to come in person, I think the exhibit will be opening up in January, like I said. So it's so inspiring to see how science can inform art, but also how art can inform science. I've had many opportunities to speak with the artists and other scientists during this process of my career, and I always find new ways to think about nature when I come out of those conversations. I mean, just recently, I think it was June during Pride Month, I was having, I mean, it seems recent, but it seems years ago at the same time because of how hard things can be right now. But I was on a call with a Dr. Cindy Lynn from Snow Lab and Joel Toms, one of the drift artists. And we were discussing the pride flag that I happen to have up behind me. And we were also discussing neutrinos, which we'll get to hear from Art McDonald, who has a pretty cool part of that story, which we'll hear about when I introduce him. During the conversation, I suddenly made kind of an unusual connection that these neutrinos, which were showed by snow, that they oscillated from one state to another, reminded me a bit of gender, in that we often have typically thought of gender as this fixed thing, in the same way we think particles maybe are fixed things. An electron is an electron, a proton is a proton. But then neutrinos came along and they're quite different. They're a little bit more like gender fluid particles where they can change their type. So anyway, the connection may seem just like a cute allegory, but I think it's important to realize that sometimes how we view social norms and experience periods of expanding our horizons or definitions, we may find their parallels in science. Humans are weird. We like to label things and associate new ideas with old ones. So I find looking at art as an opportunity for me to kind of think about certain social creations, and when I change how I think about them, I think it does change how I think about scientific ideas, and they have led me to then exploring even new research questions. So that's just one personal story of how art and science mixing. And so I encourage you to open yourself up this evening to similar opportunities. Feel free to get to your art on now. The idea is tonight we're going to be hearing about some cool dark matter science, and I hope that serves as like a fuel of inspiration for you to make your art at home. But maybe some of you already have some cool ideas from what you know about dark matter or otherwise. So if you do want to get going now, then that's fair. Otherwise, we're going to have a few talks, and then we're going to have a really, really shared space where I encourage everybody to kind of share what they're doing and have conversations. I'm going to play some music and have some inspirational maybe images of different dark matter and nature to whet your creativity. So our first speaker is Dr. Guillaume Giroux. Guillaume grew up on the South Shore of Montreal and pursued musical education, both classical and jazz piano and saxophone, until his early 20s. Guillaume then completed a Bachelor of Science and then a Master of Science in Physics at the University of Montreal. And he did his PhD from the University of Bern in Switzerland, where he researched the properties of neutrinos. So Guillaume started his appointment here at the McDonald Institute in 2017 and is now searching for dark matter at Snow Lab. And at the same time, he is very much looking forward to teaching piano to his 2-year-old son, Henri, when he's older. So Guillaume, let us know a little bit about searching for dark matter.
All right, thank you very much, Mark, for the introduction and for the opportunity to give this talk tonight. So as Mark said, I'm here to give you a little bit of a science bit around dark matter, which hopefully will provide you with some inspiration to complete your artwork about dark matter. So before we even discuss about why physicists like me are searching for dark matter and how they do it, how do we know it exists in the first place? And then I'll tell you about our work in searching for it and why do we have to go deep underground to search for it. And then finally, I'll try to answer the question whether or not are we close to finding dark matter or not. So the first question, so how do we know dark matter exists? And actually the first evidences for dark matter, they came quite a long time ago. In 1937, there's a Swiss astronomer, Fritz Zwicky. He makes the observation of a cluster of galaxies. So that's the picture that's above here. So a cluster of galaxies is this astronomical object which is made out of a lot of galaxies. So the dots you see here are not stars; they are galaxies, and these galaxies are bound together in a system. They are attracted by their gravity, right? So they are very massive, and then they provide the gravitational force to hold this system together. So what Fritz Zwicky does is that he's able to, on one hand, calculate approximately the mass of this cluster of galaxies by counting the galaxies and estimating each one of them how much mass they would have. And then he's also able to measure at which velocity they are going about in the system. And if you think of gravity, it's a little bit like if you were to spin this ball at the end of a string, right? If you spin the ball very fast, you have to hold the string much tighter, right? So this is the equilibrium between centrifugal and centripetal forces. So here is the same. The galaxies are moving quite fast, but they're also attracting each other due to their heavy masses. So the system is held together. But what Fritz Zwicky finds is that there is not enough mass in the system to explain the velocities of the galaxies. So he is actually the first one to suggest that there could be a lot more mass in this cluster, which is invisible, and he's the first one to call it dark matter, actually. And if you think that this picture of him here is not very flattering, you can research a little bit about this this guy, but he was known to have a pretty bad temperament. So I encourage you to read his Wikipedia page. Now I'm there. Switching slide. Another much later observation in 1975. American astronomer Vera Rubin is now studying an individual galaxy and looking at the velocities of stars within that galaxy. So it's a similar observation, and based on the same principle that if you observe certain velocities of stars, you need to provide a gravitational force for them to be holding the galaxy together. So in a galaxy, typically most of the mass is at the center, so you would expect as stars and gases orbiting the galaxy here are getting farther and farther away, that the gravity gets weaker, so that the predicted velocity should decrease as you go farther away from the center of the galaxy. But what she observes, in fact, is that the velocities stay quite high all the way to the edge of the galaxy. So again, here, she proposed that there must be a lot of dark matter in this galaxy, forming some sort of a diffuse halo of matter that you can't see with the telescope. So that's in 1975. That's already quite a long time ago. Nowadays, we have much more indication that there is a lot of invisible matter in the universe. And not only that this matter is invisible in the sense, so here, maybe then that can be an inspiration for your art. When we say dark matter, it's not necessarily that this is black, right? Like a black object. A black object does not emit light, but a black object would absorb light. Dark matter here does not emit or absorb light. It's just not interacting with light at all. And I will not go into details of these modern observations, but basically, on one hand, we're now able to take a picture of where gravity is. And this is exploiting predictions from general relativity from Einstein. This is called gravitational lensing. And we're now able to, when we take astronomical picture, we can look at the same time where the stars are. We can look at where the gases and dusts are with the other types of astronomy, like for example, X-ray astronomy, but we're also able to take picture of where most of the mass is, and this is where the dark matter is. Another study here, this is maybe another inspiring picture. This is a very detailed study of what is called the cosmic microwave background. So this is a little bit of an imprint of very early in the universe, the density of the fluctuations in masses, and we're able to extract from these pictures very precise information about the content of the universe in terms of normal matter, like stars and galaxies and gas and dust, and dark matter, which does not interact at all. So you'll note here that both early observations with telescopes and modern observations with gravitational lensing and cosmic microwave background, we're noticing that there is dark matter in the universe, but we're only noticing its effect on gravity. So we have not detected dark matter. We were not able to pinpoint it and identify it. We were only able to see what it does to large astronomical systems due to its mass. So just a little note here. So if we are only... Hello, this is my son. If we are only concerned here about, give me a second. This is Henry here. This is bad time for him. So yes, so the question is, if we are only seeing gravitational effects of dark matter, is it that we don't understand gravity correctly? Did we make a mistake when considering gravitational forces? And this is a little joke here from this cartoon website XKCD, where it says that the motto of this Department of Astrophysics is that if you think you have a new idea, thinking that there exist laws of gravity that we don't understand yet, we have tried this already, and it just does not, it's not able to explain our astronomical observations. So it does seem like the universe is filled with dark matter. So my next question was, then why do we care about finding and identifying dark matter? Well, this is my take here, but as a particle physicist, we have defined the building blocks of everything that's around us, right? Those are the fundamental particles. And the way those fundamental particles assemble together and the forces that make them assemble together, we understand very well. We're able to explain how the elements from the periodic table of the elements are formed in stars, in dying stars, in supernova. We understand how these atoms can form molecules with electrostatic forces and form larger molecules. And eventually, we're not claiming with particle physics to explain why did life emerge in the universe, but we're able to explain a lot of phenomenon with just fundamental principle and forces and particles. But yet, when we account for the mass of galaxies and clusters of galaxies, we realize that we are missing a lot of this mass. So there seems to be a big piece that's missing from our fundamental understanding of particle physics, and this is dark matter. So to the next question, how to go about to search for dark matter? Well, the question depends on what do we think dark matter could be. There exists a lot of theories. One of them is called weakly interacting massive particles, and this is the one I will be talking about tonight. And then there is all other sorts of theories, and this is just a small number of them. So here tonight, I'm talking only about these guys, because those are the ones I'm searching for, and those are the ones that a lot of astroparticle physicists at Queen's and in Canada are looking for. Okay, so those are theorized to be particles with some mass that interact extremely weakly with normal matter and don't interact at all with light. So they're dark matter heavy particles. So if one wants to go about and try to detect those particles, you have to take advantage of this very weak interaction it can have with normal matter. So you have to build a detector, and you have to hope that eventually this dark matter particle will collide with one of the atoms inside your detector, and then go on its merry way around the cosmos again. So this is in principle, the WIMP escapes your detector, but what you're able to measure is the very small recoiling nucleus. So it steals a little bit of energy from the dark matter particle. And then if you're able to measure this little recoil in your detector, then you can say you have detected dark matter. So this is in principle, but in reality, it's much more complicated than this. First of all, the signal that we're looking for, this collision of a dark matter particle with our detector, is extremely rare. So this is the weakly part of the weakly interacting massive particles. Most of the time, it does not interact. It just goes pass right through your detector, and only very rarely will it interact. And at the same time, you have all sorts of other particles and radiation that will disturb your detector. So maybe some of you are not aware of this yet, but everything around you is a little bit radioactive, and that's not the fault of humans necessarily. There is a lot of naturally occurring radioactivity. It's very small levels, and they're not dangerous for humans, but our detectors are very sensitive, and they can be disturbed by this radiation. So for example, gamma rays or neutrons can make a signal in your detector. And lastly, as I said, what you want to detect, actually, this nuclear recoil has a very, very, very small energy, because the dark matter particles, they're not moving very fast around the galaxy. So when they do a collision, then you have only a small recoil. So what you want as a technology, you want a detector that's able to measure very faint signals of nuclear recoils. You want them to be very big to increase your chance of catching one of these dark matter particles. And you want them to be made out of very pure materials, and you want them to be shielded from the external radiation. So here I'm just showing two pictures of two dark matter detectors that were located at the Snow Lab near Sudbury. One of them is the Pico 60. It's a bubble chamber. I will not go into details, but it exploits a thermodynamical property of matter, which is called superheat. So here we are heating a liquid far above its boiling point, but yet it is not boiling because we're holding it so carefully in a very smooth quartz jar. And if a particle enters the detector and interact with the superheated liquid, it will make it boil locally. So we're able to take pictures with cameras of a small gas bubble appearing in the superheated liquid. A completely different experiment called Deep 3600. It's this giant ball. It's at almost 4 tons of liquid argon. And liquid argon has this property that if you deposit energy in it with radiation, it emits light. This is called scintillation. So this detector here is equipped with hundreds. So all of these circles around the big sphere are very sensitive photo detectors that are able to see these very small glimpses of lights that are emitted when a particle would interact with the liquid argon. So this is just 2 examples, but there exist a lot of these detectors all around the world searching for dark matter. So then why do we need to go so deep underground, 2 kilometers underground, to search for dark matter particles? It's because when I was telling you about naturally occurring radioactivity, it turns out that the most important source of this radioactivity is due to the fact that the Earth is constantly bombarded by cosmic rays. So maybe you've heard about cosmic rays. Those are high energy particles, protons mostly coming from outer space. They interact with the outer atmosphere, and then you have these showers of high energy particles that would, if we were to install our dark matter detector at the surface of the Earth in a building at Queen's University, for example, the only thing we would see is those cosmic rays. So we would not be able to search for rare signals. So in Canada, we're extremely fortunate. So we have this world-class facility called Snow Lab. This is 2 kilometers underground, under the shaft of the Cretan mine. So this is an active nickel mine near Sudbury, Ontario. And there is this vast laboratory which has many different dark matter experiments and also neutrino physics experiments. And in order to protect the experiments from natural radioactivity, this space is extremely clean. This is called a clean room, class 2000 clean room. The air is filtered, everybody's wearing jumpsuits, and the dust and the air quality is controlled to very high levels. So finally here, I'm telling you, so did we find or not dark matter? We did not. So the 2 experiments that I showed you earlier, Pico 60 bubble chamber and Deep 3600 liquid argon, they ran for a number of years and they were unable to find a signal of dark matter. So what does that mean? That means that they were able to exclude at least certain models of dark matter. So those plots, which maybe also can provide you with some artistic inspiration, are called exclusion plots. On one side of the plot, you have what we call cross-section. So cross-section is the strength of the interaction. So as you go lower are dark matter particles that would interact more rarely and more rarely. And on the x-axis here, you have the mass of the particles, so heavy or light. So for example, here, this cyan curve was with our detector, Pico 60, we were able to say that everything that's above cannot exist. We would have seen it, but everything that's under, we don't know. The detector was not big enough, or it was not clean enough or sensitive enough to search for these types of dark matter particles. And the same thing with the Deep 3600. So Deep 3600 and Pico 60, we're searching for slightly different type of dark matter. So this is why they're not drawn on the same plot here. So if one wants to then test more models, go beyond these exclusion curves and test if there exists dark matter that interact even more rarely, you need to build bigger detectors. More detector mass means you have more chance to catch one of these particles, and they need to be made also more sensitive. The more sensitive they are, the smaller dark matter mass you can search. And you also have to shield them even better from external radiation, naturally occurring radiation. So just at SNOLAB, and this is just SNOLAB all around the world, there's other labs in US and in Europe and in China, where a lot of next generation experiments will be constructed. So this is just an example of 3 large dark matter experiments that will happen at SNOLAB. The USG experiment with the spherical counter, a super CDMS, which uses semiconductor detectors that are almost at absolute zero, so they're cooled at very, very low temperature. And then there is the Pico 500 detector, which will be again a bubble chamber with the superheated liquid, but this time 10 times bigger than the previous generation. So we're hoping to be able to test much more dark matter models, and hopefully one of these experiments would be able to find a signal of dark matter. So I'd like to thank you for your attention, and I'll be welcoming any of your questions now.
Thank you so much, Guillaume. You took us on such a really cool story of kind of painting the picture of like why we think it exists and where it could be. I really, really appreciate that talk. Thank you so much. And I'm curious, do you, and I'm gonna take questions from the crowd, but I'm just a little bit curious about, I know that you originally trained as in music and both piano and saxophone. Do you feel like science is kind of, is the science that you do ever like kind of feed into the music that you make or the other art that you make, or do you find that it works the other way? Like the art that you make feeds into the science that you do?
This is a very interesting question, and this is a question I wondered often, because it's not unusual that you see in physics, you find that people have artistic backgrounds or interests. To me, one parallel I can see is the notion of creativity, right? Which is both important and when you do fundamental science, creative new ideas, thinking beyond, being inspired and thinking something, something new. This is more of an intuition, and the same happens in music. Creativity is extremely important. But for both science and music, it seems like you can only, maybe not only, but you can become more creative once you master the language, right? So if you never play piano, you cannot expect, if for example I spend weeks not playing piano because I'm busy with something else, it's harder to be creative because you're too busy wondering about the mechanics of the instrument. And it's the same thing with physics. You have to study a very long time. You have to do a lot of repetitive stuff. You have to teach. You have to learn, take courses, and eventually you master the language of mathematics, of particle physics, of detector instrumentation. And once this is integrated, just like the keyboard of a piano, then you can be inspired. Then creativity can occur. So that's the parallel I can see.
Cool. Anybody have any questions out there? You can raise your hand maybe and I'll call on you, or I see that there is a question in the chat from Michael Faubert. What do you find more beautiful, aesthetically interesting, the physical apparatus, instrument technology, or the data? For example, the images it produces.
For me, it's the data. It's the data that you end up looking so much at, and finding patterns is extremely satisfying. The instrument themselves are, I think for me, are harder to appreciate because we work on them so long and encounter so many technical problems that at the end when we look at them, we're just happy they're done and they're constructed and work properly. But the data is different because the data can always reveal something new. Sometimes you look at your data, you make your findings, you write a publication, publish a paper, and then years after you can go back and find new patterns and you can learn more things about your experiment.
Thank you so much. And I wanted to introduce the next person that we're going to hear from, who is Sunny Kerr. So Sunny, thank you for sharing your video. Sunny, you've developed numerous exhibitions, acquisitions, programs, and publications in your role as curator of contemporary art at the Agnes Etherington Art Center, with a focus on emergent issues and practices in contemporary art and experimental formats of presentation and participation. Some of your recent exhibits or exhibitions include projects by artists such as Brendan Fernandez, Chris Klein, Yam Lau, Tao Lewis, Walter Scott, and Judy Radul. And some of you teach curatorial studies in the Screen Cultures and Curatorial Studies graduate program at Queen's University. So Sunny, thank you so much for agreeing to join us this evening. I'm really looking forward to hear from you about how you feel like art and science have a bit of a place for a conversation. So I'm going to encourage you to share your screen, and I'm gonna mute away and go away. But again, people feel free to write any questions you have in the comments or whatnot.
Thank you, Mark. I really appreciate the introduction, and it is really very fresh for me right now. So I'm happy to talk about it with everyone today. And where I work as a curator at the Agnes Etherington Art Center at Queen's University is just a couple buildings away from Sterling Hall. So if you are on campus or if you're visiting Kingston and you haven't been, please come and see what we do. And of course, please try to come and see what we're making this winter in the form of the Drift Art and Dark Matter exhibition. So what I'd like to do with you today is to tell the story from my perspective of this adventure that we're going on with the McDonald Institute and with Snow Lab. As Mark said, it is, I'm gonna just press play now, hold on a second. As Mark said, it is an exhibition that was generated from a residency in which 4 artists, Canadian artists and also international artists, got a chance to visit Snow Lab, and they've been thinking about making about dark matter and exchanging with scientists, theoretical and experimental physicists, chemists, students, and others since then. And what you're seeing here is a kind of sneak preview of some of the promotional material. This is kind of aimed at an art magazine in particular, but it gives you a little bit of a taste of it. And it is also a web project. It's a book. It's a set of educational programs for learners of many ages. And it's a national tour. It'll be traveling to universities across the country after our show closes. But the process of working on this with McDonald Institute and Snow Lab has really revealed that it is so much more than just these kind of outputs or presentations. And so what I wanted to do was to take you through a little bit of the background, how this project was generated, and speak to my perspective on the dynamics of our collaboration between an art institution and science institutions. And also speculate about some of the exciting possibilities and indeed sort of urgent necessities that could determine our orientation together in the future. And so I'm showing this image because here is Dr. Art McDonald speaking with a couple of our drift artists, Josefa and Jam on the left, and Nadia Lichtig. Josefa is an artist based in Paris. Nadia is an artist, a German-born artist living in France also. Art McDonald is important to this story, of course, because in the early 2000s, he and someone you may not know named Jan Allen, who is a former director of the Agnes Etherington Art Center and my predecessor as curator of contemporary art there, worked together on a collaboration to likewise bring artists to Snow Lab. 3 artists went 2 kilometers underground and learned about neutrino physics and created an exhibition for the Agnes Etherington Art Center. And then fast forward to 2017, the Agnes hosted, building on that relationship, hosted the New Eyes on the Universe physics exhibition. And it was around that time that we also proudly displayed and still display a replica of Art McDonald's Nobel Prize and alongside the important information. So the following year, Fuad Elgindi, Managing Director, and Zach Kenny, Communications Officer at McDonald Institute, approached us in the interest of striking up a new three-way collaboration between McDonald Institute, Snow Lab, and the Agnes. This time focused on the science of dark matter. And so that set into motion our work, my work in particular, selecting the right mix of artists and our work together as a collaborative team to arrange a residency that would allow for rich encounters between artists and scientists. And so why would McDonald Institute and Snow Lab want to do this? Well, the first answer is probably the most apparent one, which is science communication. I think it was born as an idea perhaps to that creating an exhibition would allow for audiences to access or to be educated somewhat about, aspects of the highly complex physics. And yes, I think it has already, and it will continue to create new kind of platforms and or roads, avenues for understanding. The most interesting proposition, however, for us as an art institution relates to what you just heard about from Guillaume, really. It's that we're now scientists are really at a highly innovative stage in the search for dark matter, proliferating different modes of calculation, different kinds of detection. And this, for us, really signaled a kind of openness to different ways of knowing, different ways of thinking, different ways of understanding the world. And, right there is somewhere where, those are the seeds of a productive collaboration, because we are open to each other's ways of knowing. There's at least the beginning of an inkling of that. And so this is especially appealing for an art institution because artists themselves are producers of knowledge. Each artist works with ideas and material in a way that creates objects that are not just objects, but are sensitive, emotional, perceptive portals. This is just my opinion here. I've been thinking of artworks as portals to a kind of unknown. Maybe it's chaos or some kind of idea of infinity, or something outside of our everyday notions of space and time. Anyway, so that is to say that from my perspectives, artists are not interested in simply illustrating scientific concepts or processes. In fact, I think reproducing things is sort of low on the list of what artists really want to do. Artists are also searchers and researchers in their own way. Now, it's been really exciting to personally meet with scientists and to hear scientists speak about their work, and to communicate with science communicators. And it's one of the things that we've had to kind of come to grips with as we, the practicalities of working together over the last 2 years. It's clear to me that, both science and art are really kind of pushing against their own assumptions within each of our disciplines, pushing against our own orthodoxies. But the process has revealed maybe one kind of simple truth that sticks out among others, which is that our goals are different, and always were different, and always will be different. And that, for me, is a really fascinating, and I'll get to why I think it's actually one of the central important things going on here. It seems to me, for example, that science is focused on trying to refine an ever more accurate picture of an existing state of affairs. And art is not doing this. Art is interested in searching for new languages. It's interested in unfixing things or asserting the unfixedness of things. It's uncovering things that are involuntary. It's often more interested in the frames around things and dismantling the frames around things. And so the question becomes, how could we ever possibly work together? And so this is where I think we need to turn to the parable of the elephant, which you've probably heard many times, but I think it's kind of useful in this context. In one telling of this parable, you have a group of people who are blind and encountering an elephant for the first time. And one feels the trunk and says, an elephant is like a tree trunk. One feels the side of the elephant and says, oh, the elephant is like a wall. And another says, feels the tail and says, elephants are like rope. And so this is sometimes used as a parody, really, of the kind of hopeless ignorance of humanity that's trapped in its narrow individualities, trapped in its narrow kind of competing belief systems, trapped in its narrow kind of siloed disciplines also. But I think it's, you take it one step further and we can read it equally as a moment for collaboration, that would combine the insights of the different perceivers in this scenario. And it is really about what we can do together if we recognize that we are in relationship with each other. And so there's another version of this parable called The Six Blind Elephants. And in this version, there were 6 blind elephants who are debating what it is that humans are really like, and they decide to find out for themselves. And so the first blind elephant goes and feels a human and declares humans are flat. And after all the others do the same, they agree. And so Wikipedia very cleverly, it was Wikipedia where, I was looking at versions of this parable, and they very cleverly included a moral at the end of this version of the parable with a quotation by Werner Heisenberg that goes something like this. What we observe, we must remember that what we observe is not nature in itself, but nature exposed to our method of questioning. And so here too is an argument, to me it's an argument for investigating variable and variant and multiple ways of questioning. So as I understand dark matter, and I've been using the old framework of the known unknown to think about dark matter, because we know it exists, but we don't know precisely what it is, and we haven't detected it precisely. And as an invisible and untouchable matter, an imperceptible matter, it has a kind of opaqueness and opacity that I think is really compelling for scientists and compelling for artists, because it drives a questioning. But especially for artists, I think it does another thing, which is to turn us away from dark matter itself. It turns our attention to the frame again. It turns our attention to the methods, the relationships and contexts around it. And this is really, one of the reasons that I was really keen to title this project Drift. You may have been wondering why it's called Drift, Art and Dark Matter. And of course, it was suggested to me early on when Fuad and Zach were speaking about the drift, which is an actual passageway. It's a common mining term for a passageway that links different areas of a mine. And in the case of Snow Lab in Creighton Mine, it connects the lab to the elevator and to the other working mine parts. And for me, it was an instant kind of metaphor for connection. So from the very start, it's a connection between art and science, but it's also because, as Guillaume was explaining, the lab is, you couldn't ask for a better metaphor for isolation and kind of anti-context in a way. It's clean, it is shielded, it's 2 kilometers underground for a reason. But there is this drift that connects it to our moment in time, our contemporary culture. It connects it to the landscape around it. It connects us to the work and labor and the lives of people around it. And so I was really interested in that as a rich metaphor for the way in which we are turned back to thinking about the context for this search. And I have to say, it's continuing to be a rich investigation because of the urgencies of this contemporary moment. We're in a moment of terrible racist violence, as Mark was outlining at the beginning. Also, multiple, environmental catastrophes, and I think it is a key moment for science, art, and indigenous ways of knowing and being to really to open up and combine in a way that allows us to tackle the real kind of difficult challenges that we're all facing now. And so here's an image of a session we had wherein one of our drift artists was discussing her artistic work with some physicists and other staff in Snow Lab. You can see the artist Josefa and Jem in the center. She's got her hand up, kind of speaking about some of the work. And I guess I wanted to comment on another kind of implication of the word drift, which is the kind of imprecision, the kind of instability, the unpredictability of this process. We engaged on this adventure that is a residency-driven exhibition, and that means that we don't know what the artists are going to make. Now we have some idea, but for a long time everyone was really engaged in a kind of mutual exchange with no real pressure to define an outcome. And drift also means that we are losing some certainty. We're losing some certainty of meaning as things are translated from one discipline to another. But I think it also gives us a kind of freedom at the same time. And right at this very moment, the artists Joel Toms, Josefa and Jem, and Riley, and Nadia Lichtig are, in their studios, in their portions of the world, making their work. We at the Agnes are, getting ready to install the work, ship it here. We're assembling other groups of artists who are going to meet with them, organizing all of our programs, creating our websites, etc. And I'm writing a text that's going to go into a book about this project. And for me, what characterizes this moment is really this kind of unpredictability and this sense of waiting. And I would like to finish by likening it to what the dark matter detectors in Snow Lab are doing right now. They're waiting. They are also in this kind of vital dark space. For me, they're waiting with all of us drifting through space and waiting for a signal. I think that's where I'll stop.
Thank you, Sunny. I came into tonight kind of feeling like I already was kind of knowing what I was going to be creating later. I will tell you that your talk has completely changed, I think, how I want to approach my art. So I really, really appreciate that. I'm wondering, we have time for one quick question before we're going to move on to kind of the next phase, but we will have then a kind of a larger opportunity for some discussion as well. So if there's anybody that has a question, I encourage you to raise your hand or put it in the chat, or feel free to just unmute yourself, however you like to engage with us. Not seeing any questions, so maybe we'll wait. What insight from engaging with dark matter science has changed your mind on something, anything?
Has changed my mind on anything?
Like if you felt like you felt yourself change about something as a result of your work with dark matter science.
Well, let's see. I feel I am really changed by the process of this collaboration. I mean, I think that's really it for me. It's like it's become, you know, more important than any given output that we do. It's more important in the exhibition is being able to make a habit of working together, because it's if you know, if drift has another kind of significance for us, it's that we tend to kind of go back to our camps so often, and we lose the thread of our collaboration. You know, it's so simple for us to you know, come to some agreement and start to understand how a different discipline is thinking and working, and then we drift apart. You know, it happens again and again. We have to kind of leave breadcrumbs so that we can find our way back. And you know, I think partway through this process, I realized this is the valuable thing. We need to, you know, do this as if we are going to continue doing it. It's not a one-off project. We're going to make these avenues that we can use over and over again.
Thank you for that. So I think we're going to do a little bit of a transition now. So what's about our next speaker, I'm going to introduce in a second, but I know that while he is speaking, we will not have any visuals. So it's all the more encouragement for you to feel welcome to start. I know that we sent out some paints and some supplies, that maybe you're making arts another way. I encourage everybody to really feel free to get into the create mode now, and maybe reflect on what we heard and what we're about to hear, where I introduce kind of the last person that will be speaking with us about kind of art and science and dark matter. And that would be Dr. Art McDonald. So Art, if you'd like to share your video. So Art was born in Sydney, Nova Scotia, another Nova Scotian like me. And he studied at Dalhousie University and then at the California Institute of Technology in Pasadena, where he earned his doctorate in 1969. Art worked at the Chalk River Nuclear Laboratories near Ottawa until 1982, when he became a professor at Princeton University. Then in 1989, he became a professor at Queen's University here in Kingston, Ontario. And Art led the snow experiment in Sudbury starting around 2000, which showed that neutrinos can change their flavors, which I already kind of highlighted. And that meant that they have mass. This was a true kind of breakthrough in that it was not expected. And it was for this work that he was awarded the 2015 Nobel Prize in Physics. And so it's my great honor to welcome Art to the call. And I know that we're gonna kind of share some thoughts, and I really look forward to hear from you. So thanks for joining us.
Thank you. Well, one of the things to be noted in this is that what we're doing tonight, and what certainly has been done with the exhibit that Sunny is curating, is teamwork. Teamwork between the artists and the gallery, and tonight with all of you. So I encourage you to be creative in your art. And just by the way, Sunny, you know, there's a great whimsy in the way scientists do things and name things and so on. You know, there are drifts on all levels of the mind, but ever since the snow project started, of course, the drift that you showed there has been known as the snowdrift. So we've had all kinds of fun things needless to say, the big sphere of heavy water in the middle of the snow project was known as the snowball. And of course, all of us were snowflakes pretty well. So anyway, it was actually a very enjoyable collaborative experience, just as it is right now with this group. So let's try to, I'd be very interested in seeing what gets creative in the next while. And let me just give you a couple of thoughts about some of the things I was thinking of when I was given information about this project. And so in thinking about the art and science of dark matter, I was reminded of a wonderful talk given by an indigenous woman elder to a major international physics conference in Sudbury back in 2017. She spoke very eloquently about the traditional indigenous view of the universe around them. She spoke of the narratives that are their traditional way of preserving the relationships with nature and their mythology and religion. They have a very close relationship with Mother Earth, with the heavens, the sun, and the moon. And of course, they are very conscious of how human activities are affecting the earth around us. One of her primary messages was that although we think as scientists that our scientific studies are unique in providing a view of how our world works, there are other approaches that have very similar objectives of trying to understand our world, but they approach things very differently, such as the approaches taken by the indigenous people. So clearly, there are these many different ways to look at the world around us, and it's important for us to realize this. As particle physicists at the McDonald Institute, we study the entire universe and how it evolves, and we try to understand it as being created from the most fundamental particles interacting through the laws of physics. Mathematics, theory, calculations, and experiments are the essence of our work. We love symmetry in our approach to nature, and we often find it in the laws, which are mathematically very complex, but often turn out to be quite simple and symmetric once we've found the correct underlying basis for them. So I was reminded in that great talk by the indigenous elder that there are also very different ways of looking at the world around us, providing perspectives that may be much more accessible to people who don't have those many years of training in mathematics and physics that are common to our scientists and their approach. These other ways of approaching the world around us can give us very different perspectives that are worth considering and can tell us all things that we should have thought of, but maybe didn't until we saw them through someone else's eyes. A very clear example of that is the indigenous people's alarm and awareness of the climate and other changes in our world caused by human activities that are highlighted for them by their close contact with nature. So I'm looking forward to the perspectives contained in the art you create tonight and in the final exhibit, and I hope that it'll be valuable in a similar way in providing a different perspective. So the visual approach to the world will be varied and may reflect things that are beyond things that our scientists typically think about. As scientists, even, we have to remember that the framework that we use to describe this composition of the world with fundamental particles is actually totally imaginary. No one has ever seen a quark or a neutrino, although we can calculate the impact of these fundamental particles with great accuracy. This imaginary framework, in the sense that it's something that's been created by scientists and is very well defined through the mathematics used to describe it and represented in the laws of physics, is a framework. It's a human construct. And it is in fact,
Yeah.
excuse me, and it is in fact something that we use in a very valuable way to make progress and to design our experiments to do so. But it is a construct, and it is an approach that needs to be recognized as such. And having others who approach things in different ways can perhaps help us with our understanding of this, because ultimately, what has been created is something that's very subjective within the attitudes of the people who are attempting to come up with a description of our universe. So there are a lot of similarities between the way scientists and artists behave, actually, and how they approach their different topics. Scientists, like artists, are very open in the communication of their results. They want the rest of the world to benefit from their insight and to be inspired by it and to build on it. Sir Isaac Newton is quoted as saying, "I can see further because I stand on the shoulders of giants." And there are many parallels in the artistic world where art, music, theater, in their many forms, have inspired humans throughout our existence. Openness, broad communication, and even peer review have been the hallmarks of the artistic world, just as they are in the scientific world. And in the artistic world, the grand masters of the past in all of these areas are revered for their contributions. So dark matter, it's a very difficult concept to grasp, whether you're an artist or a scientist. It's what is not there so far, or maybe a better statement is it's the dark between the stars on a starry night. It is something that doesn't interact with light, and therefore we don't observe it. And that's in contrast to the stars that we, for many reasons, think are very much made up of the form of matter from which we are created ourselves. And in point of fact, stars are the origin of a large fraction of particularly the light elements from which our bodies are primarily composed. And therefore, we ourselves, in fact, are made from stardust. But the most concrete way to infer that dark matter exists is through its influence on other things, as Guillaume described earlier on, particularly through the force of gravity. Another one of these imaginary forces, which one mathematically described, does such a great job of helping us to understand the world around us in the scientific context. Some of the ideas that come out of this are really pretty unusual. And for example, the idea that you have billions of small dark matter particles, infinitesimal dark matter particles passing through you right now, steadily throughout your lifetime, and that in your lifetime, not even one of them will stop and do anything in your body. They interact even less frequently than neutrinos do. So nobody will ever see or feel a dark matter particle directly. And that's why we have to make these very sophisticated experiments to try to observe even the faintest evidence for them. But scientists are quite convinced that such dark matter particles are one way to explain the large-scale influence that we see for them in our universe through gravity. Now, creativity is also clearly a characteristic of both art and science, and inspiration is something that's necessary in both. Leonardo da Vinci and Albert Einstein each required substantial inspiration and exhibited substantial creativity. Da Vinci is still remembered as an artist, an architect, also a scientist, who was extremely creative in all of the areas where he worked. Albert Einstein put forward in 1905 what today are called, in the parlance of today, disruptive ideas that were in fact at the time so disruptive that in fact they had a tremendous influence. And Time magazine actually put him on their cover as the person of the 20th century, not because he invented the computer or the laser or even the GPS system, which, by the way, only gives you the accuracy it gives because you make corrections using general relativity from Einstein, but because those basic ideas were really helped create all of the technology that transformed the 20th century. He was disruptive, no question. And so in this way, he's similar to avant-garde painters of today who purposely try to disrupt our views of art. In earlier days, Impressionists attempted to change the way we approach art and to see new aspects of our surroundings by moving beyond pure representation of what you see around you. And sometimes in both areas, we have to challenge the status quo if you're going to make progress. I'll be very interested in how artists approach this notion of a dark substance, unseen but influencing our world in very substantial ways. So although, as Sunny said earlier, artists and physicists approach their subjects in very different ways, there are those underlying principles that motivate them both. And as Brian Greene, the particle physics theorist and popular author, has noted, even scientists working on a purely objective description of the world using fundamental particles and laws of physics end up approaching the subject in their own very subjective ways. And in that sense, in the approach to the subjects, there's one element of both artistic composition and science that motivates both artists and scientists, and that's symmetry. And sometimes in art, departure from symmetry is a purposeful approach, as is, well, pretty extreme, but seen in Picasso's work. Interestingly, this is also a strong motivating principle for scientists seeking this complete framework to describe our world with fundamental particles and laws of physics. Physicists set out looking for a simple, often symmetric framework, and are usually not satisfied by a theory that's too complicated in its basis. They want something that's quite simple and symmetric, and remarkably, in many cases, nature follows these quite symmetric laws as represented in a mathematical way. And yet many of the breakthroughs that we find in physics arise from the observation of deviations from these symmetries. So I'm looking forward to observe the ways that the artists tonight and in the project at the Etherington describe our concepts of dark matter. I won't be surprised if the approach that you take and they take brings inspiration not only to a general audience, but also to the scientists seeking answers to this very difficult question of trying to describe dark matter in a scientific way. I'm sure that one of the things that everybody will be able to relate to was actually described by Persig in Zen and the Art of Motorcycle Maintenance in his book in the 70s, which I think is known as perhaps the most published philosophical work ever, that quality in either area is something that is appreciated or can be appreciated even by people from the other area who have no training or specific knowledge of science or art in the respective cases. So I'm sure we'll all recognize the quality in what's done, and in that sense, it'll be an enjoyable experience. Thank you.
Thank you so much, Art. This Yeah, it was really interesting to hear your thoughts on you know where this direction goes when we bring art and science together.
This is kind of where I ended up. So like my original concept of just like chicken scratching ideas on the side. So like I talked earlier about like creating like an augmented reality where like you could walk into a space and activate an app and be able to see things. And I started thinking about like how that could then